Hello, everyone. Welcome to session 7 of Intro to AI-Driven Science on Supercomputers. Today, we have Sam Foreman, who is an assistant computational scientist here at the Argonne Leadership Computing Facility. And he is going to talk to us about running large-scale training on supercomputers. We also have a science speaker that's going to come in, Eliu Huerta, and he'll be here in about an hour to talk to us about translational AI as well. So with that, I'm just going to hand things over to Sam and we'll get started.
All right. Go ahead and share the screen. Get that out of the way, I suppose. Okay, yeah, so I guess I can go ahead and get started. Yeah, so as Paige said, I'm Sam, and today I'm going to be talking about large-scale training on supercomputers. And so some of this material might be, for those of you who attended last week, it might not be entirely new, but some of the example that we'll actually look at and work through will be generalizable across, using many devices and multi-node training and things like that, for example. So some of the introductory material will be overlap, but also a good review for those of you who either missed last week or might have forgotten already. So the first thing to consider is why the need for distributed training in the first place. So one of the main reasons is trying to use large batches might not fit entirely in the GPU memory. And so one way to alleviate that is to split data across workers, which also has the effect of increasing the batch size, which essentially gives the networks or your models more examples with each step. This can have the effect of smoothing the overall loss landscape and improving gradient estimators, so you get a more generally smooth gradient functions, and just having more examples essentially has the effect of smoothing out those gradients. It also may have the effect where less iterations are needed for the same number of epochs. So for example, you're going through your data more quickly. In this case, you may need to make up some other compensation. Oftentimes what's done is you can just scale the learning rate to account for this increased batch size. Some of the kind of main tricks or techniques that are used were originally introduced, and I think this is probably the first work, but there's a lot of good examples on some of the common pitfalls and things to keep in mind when running large distributed training jobs, essentially. So here is kind of a graphic that is a bit much, but there's some kind of ideas in here that are useful. So the idea of having increasing larger batch sizes has the effect of essentially smoothing out your gradient landscape. And so you can see at least there's some discrepancy between where your loss landscape is generally much smoother. And there's a lot that you can try to think about. One of the problems with neural network training and large dimensional optimization in general is that it's very hard. There's no physical intuition for things. And a lot of the physical intuitions we have for how things work in low numbers of dimensions don't necessarily carry over to problems which exist in this high dimensional space. And so there are a lot of different kind of techniques and tricks that people try to use to get around things like that. I think this was also covered last week, but just to kind of drive home this point of increasing the batch size and just running larger and larger, running training across more and more resources, across a larger number of workers, can really quite drastically improve training time overall. So this is a comparison of the overall training time for a single model at different points in time. So comparing from 2016, where training this network took 29 hours with a batch size of 256 across a single Tesla P100 GPU. Versus in 2019, you can see that using a batch size of 81,920 across 2,048 Tesla V100s gets the training time down to 1.2 minutes. And so this is 2019. I'm sure this, I don't know, I don't have recent data on this, but I'm sure that comparing numbers from today versus 2019 would also be a pretty dramatic increase, just because this is something that's being pretty actively worked on in a very active area of research. There are kind of two, so when you're trying to orchestrate or coordinate some large distributed training job, there are a lot of moving parts, and it can be the approach that you ultimately take can depend a lot on what the constraints are of your particular use case. So for example, if you're trying to train a very large model that you know, for example, won't fit on a single GPU, you might have to use what's called model parallel training. I don't know why these slides are. Maybe if I turn off my video, actually. Okay, so as I was saying, they're kind of the approach that you ultimately take for your training job can depend a lot on the specifics of your use case. And so if you're, for example, trying to look at training, right. So as I was saying, the approach you take to running your distributed training job can depend a lot on the specifics of what you're trying to do. So in the instance where your model might not fit on a single device, and in this case, you have to distribute the model itself across multiple GPUs. This is what's known as model parallel training. And so this is typically more complicated to implement and is a bit more of a specific use case, but has grown somewhat in popularity with large language models and trying to train models that don't necessarily fit on a single device. And so, yeah, as I was saying, this is a suitable approach when the model that you're looking at is too large to fit on a single device. And in this case, what you do is essentially distribute the model over different devices and send the data through in batches and compute things using the weights, using whatever weights you have on your device. So there's an example on the next slide. It'll illustrate this a bit better. When doing things using a model parallel approach, you need to be careful about how you handle your communication and when data is transferred between devices. And so this is actually a bit more involved than we'll go into today, but you can imagine that it gets pretty tricky, it gets pretty complicated pretty quickly. Just to illustrate this maybe a bit further, you can consider a very simple example. So suppose we want to calculate this quantity y, which is just the sum of three different terms. So we calculate the first product, W0 with X0, W1, X1, and W2, X2. And if we suppose that each device only has one of these weights, so in this example, weight 0 only exists on GPU 0, W1 only, or GPU 1 only has access to W1, and GPU 2 only has access to W2. And so to do this kind of step by step, GPU 0, which has weight 0, will receive as input X0, X1, X2. And all it can do is calculate this first term, W0 times X0. So it will calculate this, say it's Y0, for example. And then using this piece of data, it will then send it to GPU1. GPU1 now can calculate these first two terms, essentially, since it has the output of this W0, X0, and it can use that, and then it can calculate W1, X1. So this will, GPU0 will send all of its data then to GPU1, allowing it to calculate this second term. And then similarly for GPU2, which will compute Y1 as the product, as this first term plus the second term, and then eventually it will be able to compute this should be a sum sign. This should be replaced by a plus, but finally, once GPU 2 has all of the information from GPU 0 and GPU 1, it can then calculate the final output. And so this is a pretty trivial example, but you can imagine if this were across multiple different GPUs, if you didn't just have 3, for example, and you had to worry about when and where different parts of your model can be calculated, it gets pretty complicated pretty quickly. So what's often done instead, or what is a more commonly used approach, is what's called data parallel training. And in this example, so data parallel training is typically easier to implement, and there are a lot of existing frameworks that allow you to take your existing code and run it in a data parallel fashion relatively straightforwardly. So Horovod, which is what we'll look at today, for example, but there's also DeepSpeed from Microsoft. PyTorch comes built in with DDP, which is their distributed data parallel library. And so there are a lot of different frameworks that offer more or less this. One second, let me calm down my dogs, sorry. I suppose this might also be a good time to see if anybody has any questions about anything so far. I know I've kind of been blowing through it, but hopefully some of it should be a review. But if not, I can go ahead. I guess I'm not watching the Slack channel, so if there are questions in there, I'm not seeing.
There's some people already working ahead and trying to run on Theta GPU. So is there a virtual env in the installation that they're supposed to use?
Yes, so there should be, there is a virtual environment. So the main shell script should have, should automate all of that setting up and installing everything. Yeah, if there, hopefully if anybody has any questions, they can get it resolved in the Slack. Otherwise, I will definitely get to that, the details of running everything in a little bit at the end of this. So hopefully if anybody has any problems trying to get it ran now, they get it worked out in the meantime, but otherwise I'm more than happy to look at that when I get to it. Is that okay? Any other pressing questions I should address before I move on?
Nope.
All right. Okay, so yeah, then the next thing I was going to talk about was data parallel training. And so there, as I was mentioning, there are a lot of existing libraries and tools that you can pretty quickly take advantage of and port yours that allow you to get your existing codes up and running relatively straightforwardly. And the basic idea behind this is using some mechanism for splitting up your data set. There are different ways of doing it, which I'll touch on in a bit, but using some way of splitting up your data set, you essentially feed unique subsets of your data set to different workers, which each contain an identical copy of the complete model. And then they do some global communication to keep things organized and updated straightforward. So as I was mentioning, in this example, each worker gets a copy of the complete model. And the global batch of data gets split into unique mini batches or distinct subsets. Using the local subset of the data, the model on each worker essentially takes the input and computes an output. And then the output from each of the separate workers is then averaged and used for updating the gradients in the backward step. So here's just another example, maybe to see it a bit more clearly. So you have some input data set that gets split into unique subsets that then goes to identical copies of your model, each on different workers. So in this example, 3 different GPUs. Each model then calculates some output and computes some gradients. There's then this global averaging that happens. So all of the outputs and gradients across all of the different workers are averaged, and those are then redistributed to each of the different workers and used to update the weights of their local model. Oh yes, this is essentially just another way of saying it. So really the idea of this being data parallel is that the idea being that you parallelize the different components of your data set. So you split it up into distinct subsets, which then go on to feed each of the different workers, for example. Yeah, and so once you have each worker receiving this distinct set of data, they can then kind of all communicate with one another, get some average values, and then use that to update each of their local copies of the model. That's just kind of another more complicated diagram that for the sake of time I'm going into, but it's essentially the same idea. One thing that is important to keep in mind or to make sure that you're doing when running data parallel training is to broadcast the initial state at the start of training. So whenever you're beginning training or restoring training from some checkpoint, you want to make sure that all of your workers are initialized consistently. And you can do this by essentially loading your checkpoint or broadcasting your model and optimizer states from one individual worker to all of the rest of them. And so this is straightforward in Horvath and the rest of the libraries as well, but you just essentially might want to make sure that everything gets initialized consistently so that so that essentially all of your weights and updates are then consistent from then on, essentially. There are some kind of the importance of these different pieces of advice is a bit dependent on the scale of the model that you're looking at. So when you're running relatively small training jobs across a relatively few numbers of nodes, the effect of using MPI for file IO and things like that is not as important. But as you begin to scale up and look at scaling large models across, across like the entire system of Polaris and things like that, it becomes really important that all of your communication is well orchestrated and that you are taking advantage of the built-in optimizations that exist on the whatever resource you happen to be using. So yeah, for example, you want to always, in general, you want to try to use MPI, so a distributed IO library when reading data from its own file, which we've seen in the previous weeks. And really you want to make sure that you are doing this in such a way that you have high utilization of all your workers and that things don't kind of sit idle waiting for data or waiting for updates or whatever the case may be. And so one kind of important point in this is that computation obviously stalls during communication. And so one of the important points for effective scaling is to keep this communication to computation ratio small. And so this obviously becomes more important as the number of workers and the number of resources we're looking at increases. So some things that you can do to take advantage of what we already have. So file striping on Lustre can offer pretty dramatic improvements, especially when you're trying to write to large files, for example, or when you have many different ranks trying to access different files on the Lustre file system. So this is a link that has additional resources on how to take advantage of that and what different use cases it is useful for. And then also you're going to want to make sure to use the correct optimizations for whatever system you're on. So the general best practices and tips advice on Aurora will be different than they are for Polaris, which is also different than they are for Theta GPU, for example. And so you definitely want to make sure that you are taking advantage of the correct environment variables and different settings for distributed communication and things like that. So these can actually have a pretty large effect. Again, this effect is going to be dependent on the size of the job and things like that, but definitely something that you're going to want to keep in mind and take a look at as you begin to scale your jobs. Additionally, you're going to want to preload data when possible. So offloading data to a GPU frees up CPU cycles for loading the next batch of data. This is something we've, I think, seen in previous weeks. So this is one way that you can coordinate your work effectively in order to minimize your I/O latency, for example. A kind of comparison. So yeah, this is just a diagram illustrating the difference between model and parallel. They're the data parallel and model parallel approaches. So in the data parallel approach, you can see each one of the worker has the complete copy of the weights, but only receives some subset of the data. And in the model parallel approach, it's the exact opposite. So each worker is able to see the complete copy of the data, for example, but only receives some subset of the weights. And so that's kind of the, at least in my understanding, an easy way to keep them straight, I guess, thinking about what is actually parallelized over the workers, or at least, I don't know, that's how I remember it, at least. So now we'll look a bit more closely at what specifically needs to be done in order to use Horovod for distributed training, which is what we'll look at in this example. But for those who are interested, there are examples using different distributed training libraries in some of the older workshop, in some of the GitHub spaces for some of the previous workshops. So I think there's a link maybe in the GitHub repo that has links to those. So you can look at those as well if you're interested. But today we'll focus primarily on using Horovod with TensorFlow. And so this is a brief overview of all of the different steps that you need to implement to take advantage of this distributed training. So the first being that you need to initialize Horovod and assign GPUs to each rank. You're going to want to scale the initial learning rate by the total number of workers you have. And so I'll go through all of these in detail on the following slides, but just as an overview of kind of what you need to keep in mind. You also need to distribute the gradient and broadcast your state. So this can be done in TensorFlow by wrapping this tf.gradient tape with Horovod's distributed wrapper, essentially. And then again, making sure that you ensure consistent initialization across workers. You're going to also want to make sure that your workers are always receiving unique data sets. Since if you have two workers, for example, that are receiving identical data, they will then have identical outputs and get the identical gradients, and so you're not actually getting any advantage from doing that, essentially. You're also, another important point is that you're going to want to take global averages of quantities that you are interested in. So your loss, accuracy, for example, that can be done again just using the simple all reduce function, which is built into Horovod. And then one final thing to maybe keep in mind is that you want to make sure that you're only saving checkpoints or really doing file IO in general from one individual worker. And that is important in the case where you have multiple workers all trying to write to the same file that gets corrupted or causes your program to crash, for example. So now,
Sam, we have a question. We have someone's hands raised. Thomas, do you want to go ahead?
Yeah, sorry. Quick question. So I see that for most of the code we've looked at so far that deals with multiple workers, all of the broadcasting and like file IO and stuff like you just mentioned all happens from worker 0. But would there be any sense to pick basically a random worker each time to do the broadcasting, or is the 0 just really like a convenience, or is there a specific reason to always pick the 0th worker, the first worker?
So I'm not positive about this, but I don't think that there is any reason why it would need to be rank 0 necessarily. I think as long as if you wanted to, for example, do it always from, I don't know. So I guess actually in the case where you only have one worker, that worker will always be worker 0. And in that case, you're guaranteed that things will behave as expected. I guess if you were to maybe do, use a random integer, which is from 0 to the number of workers minus 1 inclusive, you could do something like that. But yeah, really, I think it's, just
it's just convention.
however,
You'll
yeah,
get
kind of like
people
convention,
will
exactly.
look at you
Mhm.
strangely if you use a different
Yeah,
way.
exactly.
There's no advantage.
Mhm. Yeah, convention is exactly the word I was looking for. Yeah, exactly. So I mean, if you wanted to, there's nothing necessarily that it needs to be from worker 0, but again, yeah, it's just something, it's convention, and usually you have enough other bugs to deal with that it's best not to introduce things that might confuse you later on, which we all fall victim to, I'm sure. But keeping that to a minimum is generally probably best practice.
I would say that it's convention, and if you want a random master for every iteration, you'll need additional code, and also as Sam alluded to, if there were some issues, you have to know why that occurred, from who was the master over there. But again, you could always change your master to be, or the process where you aggregate all your gradients to be a random node, but you would have to build the logic to do that as part of the code. You could do it.
Yeah, that's another good point. And so I guess it's actually maybe somewhat related to that question. So sometimes so in the case where you're broadcasting and aggregating data and things like that, it's generally advised to use rank 0. But for example, if you have, after the training is finished, and you have your model saved and things like that, one thing that you can do that I've seen done is using different workers to then perform different tasks following training. So you can run inference, for example, on 4 different workers in parallel, and then handle file IO accordingly. But there are things like that you can kind of use specific GPUs for certain tasks. Also kind of, you need to be consistent in how you do that everywhere, but yeah, there's nothing stopping you.
Okay, thanks.
Sorry, I apologize about that. My guard dogs always got to keep me safe. Right, so then now I have kind of some additional details on how this is actually done in practice. So the first thing that you need to do when using Horovod TensorFlow is obviously import the library and then call this Horovod init function, which initializes Horovod and gets things ready for the distributed communication. And then you want to set 1 GPU per process ID, or Horovod calls it a local rank. So in TensorFlow, you can get a list of all of the available physical GPUs using this function here. And then this is just kind of a artifact of using TensorFlow, just something that you need to do. And then essentially for each whatever rank your code is actually running on, you will get a unique integer from this function. And then what you do essentially is tell TensorFlow that I am working on the GPU indexed by whatever my local rank is, and the physical device is a GPU. Essentially, so you get Horovod will tell you the list of all physical GPUs available, and then you tell TensorFlow that I am this local rank integer, and this is the device that I will be using, essentially. Once Horovod is initialized and the workers are all kind of set up correctly, the next thing that I mentioned you're going to want to do is essentially scale your learning rate, your initial learning rate, by the total number of workers, which is done to account for this kind of increased batch size that's due to having multiple different workers. The main, so this next step actually kind of includes the main modifications that you'll need to make to your training step function. So you have some function that takes as input, whatever data I'm looking at, the complete model, your loss function, whatever it may be, your optimizer, and then whether or not this is the first batch of data we're looking at. And so, for example, if your data is represented as a tuple of the actual data or the X and Y data batch and target, as is always the case, which I think we've seen many times by now, we compute the output of our model wrapped inside this TensorFlow gradient tape, as always. And then in order to tell Horvath how to distribute the gradient, you wrap that TensorFlow gradient tape and this Horvath distributed gradient tape. And then essentially proceed on as normal. You take the gradient and then apply those gradients to the trainable variables in your model. One thing that is different about Horvath in this example is that we have this additional argument first batch. And so this goes along with what I was mentioning earlier, where we want to make sure that everything is initialized consistently. And so if the data that we're looking at is indeed the first batch, we want to make sure to broadcast our model variables from rank 0 to all of the rest of our workers, and broadcast, and then following that, broadcast the variables of our optimizer as well. Other than that, the training step is identical to what we've seen before, TensorFlow. So again, you just compute the output of your model and then the loss function wrapped inside the gradient tape. But with Horvath, you need to be sure to wrap that with the distributed gradient tape and be sure to broadcast the model and optimizer state at the beginning of training. One of the other points I had mentioned in the overview slide was that you need to make sure that each of your workers are receiving unique data at each training step. And so there are two ways. So this is something we've seen before as well, but just to kind of drive the point home, there are essentially two ways of dealing with this. So the first way being you can manually ahead of time partition your data into different subsets and then make sure that each worker only ever receives some local distinct subset of the complete data set. And so that kind of takes some upfront coordination, and you need to be kind of clever about how your data is split up. Or a more kind of naive approach maybe would be to, from each worker, just randomly select some mini batch. For example, if your full data set is broken up into smaller mini batches that are indexed by some integer, you could, for example, randomly select an integer and use that set of data. That's I think probably less generally advised, because in that case you also have the additional complexity of having to deal with the random number generators on each of your different workers, because you want to make sure that they each start their random number generators from a different seed essentially, and so that they will always consistently get different subsets. But this is a bit more involved and is probably more prone to failure. So it's usually, if you can get away with it, probably advantageous to come up with a plan or method of partitioning your data and dividing it into distinct subsets. So this can be done, for example, if we're looking, so if we are just looking at a simple MNIST example, for example, which is built into this TensorFlow Keras datasets. We can just load the data using this command here and break it up into training and test data sets. And so the point here being that when we're constructing our test data set, we want to make sure to shard it essentially across the number of workers, divide it into the total number of workers, different shards, and send the shard indexed by our current rank to this worker. Essentially, since this will be ran on the individual worker indexed by this rank, by doing this, essentially, we make sure that each of our workers only receives some smaller subset of our complete test data set, which is determined by the index of our worker. So the example that we'll actually look at the end of this is a bit more involved and follows the data loading practices that we've built up over the previous weeks. But just as a kind of basic example to see how this can be done, you can look at it here. Okay, yeah. The other kind of main point or thing to keep in mind is that when we're calculating quantities of interest, so loss or accuracy, for example, you want to generally be sure to get a reliable estimate of your average. For example, you really want to be sure that you're actually taking the average across all of your workers, and this can be done by using this all reduced function Horvath, which is pretty straightforward. But again, yeah, it's just something that you want to keep in mind when dealing with distributed training as opposed to training on a single device, for example. So I think I was probably going to try to wrap up about now and let people start to try to run it and open it up for questions and things. But here I've got included just an overview of kind of a file system view of what's in the folder for this week. So again, we have the same functions for dealing with the data as we've seen them before. And now things have been kind of broken up a bit into this main, network, and trainer Python files, which I will go through in a bit more detail after we come back from the break. But this is kind of the structure and how things look. The details of running the training are defined in this config.yaml file, which can either be changed directly in this file or overridden from the command line when running. And yeah, so I will go in a bit more detail and look at how to actually run things when we get back from the break. Right, so there's a breakout room and then the talk. Right, I'm just trying to make sure my timing is right. I'm on schedule. Okay.
Yeah, so we have another 10 minutes before we actually go to just like full break, so people can like get up and walk around. And so if you want, we can sort of launch people into breakout rooms to start things right now. Bring them back in about 10 minutes, give them a break, and then we'll have our science talk at 4.
Okay, yeah, that was what I had in mind as well. I just wanted to be sure. Yeah, so people can try to go ahead and get it running. So there are instructions here in the slides, but this is all also, there may be more detailed instructions for getting it running here. They're also included in the GitHub repo as well. So yeah, if people have questions about anything now, feel free to ask. Otherwise, I would say, yeah, go ahead and try to get it running. I don't know what the current reservation, how the current reservation has the nodes broken down on Theta GPU. So this example is obviously designed to be ran on multiple nodes. But given that Theta GPU doesn't have all that many nodes available, you might be a bit limited in how well you can do it. Run it on things at the moment. But if you can try to get it running on whatever kind of resource you can get allocated for now, and then throughout the week, try to run it on larger number of nodes, for example.
Cool. Okay, so I'll send people into breakouts, and we'll come back in, I think, 8 minutes, and then go to break as well. I think I'll open the floor up to any questions that people might have before we go to break that came up during the breakouts. All right.
It's really slow, actually. So still.
Will you say more? What do you mean? What's really slow?
So I was running, but still, I mean, initially I saw the beginning of the batch that running the file, but then again, when I refresh it and want to see whether is there any updates, still it's keep loading. I don't see anything on the screen. Yeah, but I was able to run for sure.
Were other folks having the same thing?
Yeah.
So if you, I will send the command in the Slack channel, but it should be writing the output directly to a log file. So you might not see anything directly on the screen. I'll send the command that you should be able to see.
So I actually, as you said in the tail part, so which we are storing in the log file. But still log file shows initially what setup we made it, and then still I don't see the output results. Maybe it's still running, Sam. I don't know.
The file system's really slow today. A lot of people have been seeing, even it's just hanging on import. Unfortunately, that just happens sometimes with these shared machines.
Okay, I think with that, we'll take 8 minutes and we'll come back at 4 p.m. for our science talk from Eliu. All right, welcome back, everyone. So we're going to have a period of time for our science speaker now. So Eliu Huerta is the lead for translational AI as part of the data science and learning division at Argonne National Labs. He has a background in theoretical astrophysics, and he's done a lot of work at the interface of physics-inspired AI, scientific visualization, and extreme scale computing. So I will hand it over to Eliu a little bit more for him to start, introduce himself a little bit more, and start his presentation.
Hi, thank you. All right, so let me share my screen, and hopefully you will be able to see my slides. Can you see them?
Yep, they look good.
All right, well, as Paige mentioned, I have some interest in developing AI tools for a variety of domains, but in this presentation, I'm going to just talk about one in physics. And so these are the type of things that I am interested in and that I have worked in the last few years, from using ground-based detectors to detect gravitational waves, to using electromagnetic observatories to study galaxies and star clusters with the Hubble Space Telescope, or using other observatories to study high-energy physics and astroparticle physics. I'm going to focus just on gravitational wave astrophysics in this presentation. And let me just highlight that to get insights into this phenomena, since we cannot produce black holes here on Earth, we need to use extreme scale computing to understand them. And so in this visualization, what you see is the numerical solution of Einstein's equations to study how black holes orbit around each other, how they emit gravitational waves. This removes energy from the system, and they gradually spiral into each other, and then they eventually collide and emit a burst of gravitational waves. Now, the parameter space that describes these black holes is high dimensional. As you can imagine, you need to take into account how massive they are, how fast they are spinning, their location in the sky, the shape or orbit that they have as they orbit into each other. So there are many parameters that you need to take into account to properly describe these systems. But what we know is that these objects do exist in nature, and since the fall of 2015, we have detected tens of them. Now, back in 2017, when we discovered for the first time electromagnetic waves and gravitational waves emitted by the collision of two neutron stars, I collaborated with various people, those that were in the LIGO scientific collaboration, searching for gravitational waves, in the computing area with people that had developed the Open Science Grid, which is a network of computers that are available for scientists to use when they are idle. And then combining all these different pieces to demonstrate that this signal that was describing the collision of two neutron stars was actually in experimental data. And so I worked with them combining Blue Waters, which at the time was the largest or most powerful supercomputer for open science in the US, and then the LIGO data grid and open science grid, etc. And we demonstrated that the signal was in the data, but we had to use about 2 weeks of computing just to process a few seconds of data. And what that made clear is that if we were to discover the gravitational waves at the rate that we are doing now, many per month, the paradigm that we had at the time of using dedicated high throughput computing for this grand challenge was not enough. And so working with my team at the time at the University of Illinois at Urbana-Champaign, we decided to take a different approach, which was, let's not consider traditional or established tools like template matching, and the idea of trying to describe experimental noise, because that was very complicated. As you can see in this slide, the type of noise that the LIGO detectors observe is non-Gaussian and non-stationary, and it is plagued by this type of noise anomalies, and they obscure or even mimic true gravitational waves. So trying to process this experimental data and actually extracting weak signals from a noisy background is super hard. So what we did was to break down the challenge, explore whether neural nets provided an avenue to enhance the science reach of large-scale scientific facilities. And so we started by developing a basic neural net. And we demonstrated that this approach provided a lot of benefits compared to traditional methods like template matching. And what was the difference? Well, if you know a little bit about neural nets, the difference is that in template matching, you have a large bank of potential signals that you're trying to find in your experimental data sets. And then you need to filter the data and then overlap your data with all the different potential signals. If your template bank, as in the case of LIGO, has nearly 1 million signals, you can imagine that the process is going to be super slow. But when you train a neural net, what you do is you expose a neural network to all these possible signals with multiple realizations of noise. And then there is a hierarchical learning. At the end of the training, you discard all the signals and you end up with a compact neural network that has all this knowledge. And so when you feed in data, you can process it faster than real time. And so when we presented this to the community back in 2016, well, there were a lot of, positive and also skeptical comments about this. And the first comment was that we were presenting this as a prototype using simulated data, not real LIGO data. And so after publishing this paper, we decided to go and take on that challenge, which was creating neural nets with real LIGO data and demonstrate that these nets retain the same capability of processing data, experimental data, faster than real time, and that they were able to find real signals. And so we did it, but there was something else to do. When we presented this proof of concept, we only considered the masses of the black holes, and now we had to do something more realistic, taking into account how fast the black holes were rotating or spinning. And there was, as you can see in these boxes, a major difference, because for the prototype, we only needed 1 GPU, 3 hours of computing, and about 40,000 model signals that you can produce very easily. Taking into account now the spin of the objects, we had to use about 30 million signals. And if we continue to use just 1 GPU, we would have to train the model for about a month. That was not good, so we decided to start developing skills for distributed computing, which I'm sure you are going to learn or you have learned about in this course. And the idea is that you're going to distribute the data to multiple nodes, to GPUs, and then you're going to accelerate the training. And we started with baby steps using only 64 GPUs. We learned how to do this. And then we moved to the Summit supercomputer to use over 6,000 GPUs. And with this approach, we translated that 1 month of training into just a couple of hours. And during that learning period, we also learned how to design neural networks that incorporate physics principles, like what are the type of black hole predictions that you're going to see in the behavior of the spins, the type of gravitational waves when they are emitted, how that affects the energy of the system, etc. So we incorporated all this knowledge into the architecture and the training schemes that we used. And in this paper, we demonstrated that that provided an advantage over traditional methods, not only speed, but also doing new physics. Okay, so having done this, we return to the problem of trying to find gravitational waves using deeper signal manifolds. And we showed that using real data in these high-dimensional manifolds, we reduced the number of misclassifications from 1 every 200 seconds to 1 every 2.7 days, which was very good. We went the extra mile, and now we came back to Summit and trained tens of models using 1024 nodes, and selected 4 of them, the best 4. And then we did this ensemble analysis. You feed in data into the 4 models. When all the models agree that there is something exciting in the data, we do post-processing and then identify a real event. After doing this, we publish the models in this platform that is supported by ALCF, the Data and Learning Hub for Science, and then ask our friends at the University of Chicago to do the analysis on their end. So we had used the HAL cluster at NCSA to do the analysis end-to-end, but they connected the DL Hub to HAL using Funcase, which is this fire and forget service. Basically, you start the workers, you do the analysis, get the results, and you say goodbye. And so using that approach, they were able to demonstrate that they could process 1 month of advanced LIGO data in just 7 minutes. And as you can see here, they were able to find all gravitational waves reported in that month with no mistakes. And so that was pretty cool. We were able now to process data much faster than real time and make no mistakes. And the beauty of this approach is that since we released those models back in July last year, they have been invoked by several members of the community over 100,000 times. And this led to some press, and people were excited about using this work, these AI models. How am I doing with time? Do I go on or should I stop here?
I think if you have a couple more minutes, you can go. If not, I think we could stop and make time for questions.
Sure. So let me just add something else, that once you're able to do this type of work, the key to really do something meaningful is automation. And so what we did was to automate this process of training models in Summit using several GPUs, then using metrics like the ROC curve to compute the true positives and the false positives in the models and then select the best. And then we used a tool for accelerated inference, which is the TensorRT tool. Basically, you compress and quantize the model. And then we deploy this tool in the Theta GPU supercomputer that you are using for this training. And then we use the entire machine to, again, go and process LIGO data. And what we found is that using this approach, we were able to process LIGO data over 50,000 times faster than real time. And I saw that Huijo was in the audience. This is work that we did with him. And the beauty is that now we can go and process very long data sets. In our case, we processed 5 years long of advanced LIGO data, something that had never been done in the literature with AI. And we demonstrated that we were able to process this massive data set in seconds, having a mistake rate, if you want, a number of misclassifications of 1 per month. So this is the state of the art right now in this type of work in the literature. So I'm going to stop here. If you have any questions, please do ask me.
Thank you, Eliu. So we do have a couple of questions coming through in Slack. One of them, Alfred asked, how much data is 1 month worth of LIGO data?
So that's a really good question. You can see here the bits in green tell you when you have the two LIGO detectors, the one in Livingston, Louisiana, and the one in Hanford, Washington State. When the two of them are working, we call that uptime. So that's when it is green. And when one of them is down, or the two of them are down, that is in gray. And usually you have, duty cycle that is between 70 to 80%. So multiply a month for that duty cycle, and that's about 1 month of LIGO data.
Wonderful. Another question from Catherine. Could you talk a bit more about how you incorporated the physics domain knowledge that you have into the machine learning model?
Sure. So that was for this paper. And so here the idea is, from numerical relativity, we know about some expressions, mathematical expressions, that tell you what is the combination that the spin of the black hole should follow, okay? And so what we did at the level of the architecture is that when the model is processing data, we tell the model at the architecture level to check for this consistency. If the spin of black hole 1 is S1 and the spin of the black hole 2 is S2, you need to check that this correspondence is right. And then it is as if you were doing a matrix in the neural nets. And it just happens that in analytical relativity, we have two of those relations. And so we were doing this consistency check at the same time. On the other hand, when you're optimizing the model, you know that we use something called a loss function. And so we introduce penalty terms so that we tell the model that it shouldn't go outside of some given constraints that the model should have. And how that also translates into the energy that is released through gravitational waves. And so when the model wants to go loopy and predict spins that go outside of that range, we stop that and then we push it in the right direction.
So potentially sort of adjacent to what you just said, Alfred asks, ages ago, LIGO used match filtering to look for signals. Are you still using match filtering? Can you say a bit more about how you use AI to identify a signal?
Yeah, so the LIGO community continues to use template matching, and it is one of the two approaches, broadly speaking, that they use. The other is on model searches. So for physics that we don't understand, but there is something that is very loud in all detectors at the same time, that means that something exciting is happening, even though we don't know the shape of that signal. But what is happening at this time is that these several initiatives across the globe that we started a few years ago are finally bearing fruit. And so last year, we organized an international machine learning challenge, bringing people from Asia, Europe, and the US. And we delivered all the tools to the community to do this type of work. Now, there is also some sociology here. For some of these big collaborations to accept this type of work that is new, you need to go, with baby steps. They have the models, they have now the computing accessible, and by doing the work that we did here of releasing these models through DL Hub, and then showing them how to harness all of these resources, that is the key to enable not only members in a collaboration, but the broader community to take advantage of this type of tools. And then it is like a tsunami. Eventually, the tide is going to be so strong that you cannot stop it. And while there are many initiatives inside LIGO that are now pushing this type of activities, harnessing the models that we share with them.
Wonderful. So you obviously applied these models to LIGO. Have these models been applied to other systems, either by you or other folks in the community?
Absolutely. Yeah. So many of the models that we have released have been used in Kaggle competitions, and people have been able to reproduce our results. And in the most recent machine learning challenge that I mentioned, there were models from around the globe. And people that are internal and external to LIGO are finally confirming using their own hands that these type of results are real. And that is the main thing, the main interest in releasing these models, that people can verify by themselves that the statements that we make in these papers are for real, that there is nothing hidden, that everything is at their fingertips to go and reproduce and then use for their own work. But it it is important that you realize that LIGO data is available to anyone, not just to LIGO scientists. And this is the beauty of having this open community, that anyone can go and use that data and perform this analysis as we have done.
Wonderful. So Karthik sort of asked this, the similar question. Are there any specific other astrophysical problems that this has been applied to? Yeah.
You mean AI or
Usually the model that you have, like generalizing the model to other astrophysical problems.
Oh, yes. So, I can go ahead in my presentation. We have applied this, for example, to regression, which is parameter estimation. And so in these signals, you see that they vary when you consider something called higher order modes, which is like when you do Gram-Schmidt decomposition and you add more and more terms. So that is using higher order modes. And we created this model. The WaveNet is what we use for the detection. But if you insert normalizing flow, you can do parameter estimation. And let me show you here the important bit in regression, that when you have black holes that have unequal masses or mass ratio, it is basically impossible or hopeless to measure the spin of the lighter object. This is using the state-of-the-art pipeline that LIGO uses for parameter estimation. You cannot say anything about the spin of the secondary because the thought is that since it is a lighter object, the spin plays no role in determining the shape of this signal. But what we show is that AI doesn't care about what Bayesian inference can do or cannot do. It can predict some really good results, these very sharp probability distribution functions that agree with the ground truth of these signals. So in different words, AI is not only accelerating this analysis by orders of magnitude, it is enabling new physics, because when you know the spin of the two objects, you have additional insights about how they were formed through several astrophysical channels. So the beauty of WaveNets is that you can tweak it for a variety of applications, not only classification, but also regression and forecasting. But maybe there is no time for that.
Thank you. Yeah. So I think we've run into time, but I want to thank you for coming and speaking with us today. Thank you so much, Eliu.
Sure.
All right. So now we will hand things back over to Sam.
All right. Yeah. So go ahead and share my screen. So I've seen some people have already tried, or it seemed, from what I can tell, it seems like some people have been able to run things successfully and some people have been running into issues. So I will go through it now live. Hopefully it works and maybe resolves any questions or problems other people were having. So you should make sure you are in this large-scale training subdirectory, and then I guess I can go through the thing. So it should hopefully things should work as they are, but I've seen some people have been having some issues, so I will hopefully run this correctly and successfully. So I'm currently on a node of Theta GPU, one of the big mem Q nodes. So it's a full node and has all 8 GPUs, as you can see here. And so this, I have a Jupyter notebook and that shut down. So I'll free up that memory. Now hopefully nothing should be running. Okay. And so the bulk of this main shell script, the main kind of command line entry point for running the training, might be a bit confusing at first glance, but should clear out this formatting too. Doesn't always look as nice for everybody else as it does for me. So essentially what it does is first tries to So this was originally designed to be ran on Polaris, but then maintenance kind of complicated that a bit. And so here we are on Theta GPU. But the kind of first thing it does is we'll try to determine whether or not it's being ran on Theta GPU, which is done by checking if this host name begins with or contains this string. Or yeah, actually it is if it starts with. So if your host name starts with this string theta, then it will try to basically do Theta GPU specific information. So it will load this kind of module on Theta GPU, activate the base environment, try to determine the total number of nodes available by looking at this Cobalt node file, which is essentially, hopefully you guys are all familiar with this, but just for the sake of completeness, this Cobalt node file just has a list of all of the nodes that your job is currently running on. I think this is redundant. I'm not going to change things too much now. This just sets your host file to be that Cobalt node file. This line is kind of a clever trick to try to determine the number of available GPUs on whatever resource we're currently looking at. So this basically takes that output from NVIDIA SMI and counts the number of unique lines and uses that to determine the number of GPUs on each node. It can then goes on to calculate the total number of GPUs by just multiplying the total number of ranks, which we got from this line above, and multiplying it by the number of GPUs on each rank to give you the total number of GPUs. This is a line which makes sure that we are using the correct MPI run, which should be the default on Theta GPU, but is you need to be a bit careful because Polaris actually uses MPI exec. So we need to be sure that we're using the correct MPI command. And then we essentially format the argument to that MPI run command. So just set the verbosity to help with debugging, specify the total number of GPUs, the host file to use for MPI run, the number of GPUs on each rank, and then some environment variables that we explicitly set to make sure that each of our workers receives the same environment. And then the final thing is it defines this virtual environment directory, which for the sake, just to make things a bit clear, I tried to make separate virtual environments depending on which resource we're running on. So this is broken up into some virtual environment directory, specifically Theta GPU, whereas on Polaris, it's named after Polaris, obviously. The process of going through the setup for running on Polaris is essentially the same. We set some environment variables unique to Polaris. Again, count the total number of nodes our job is running at by looking at the number of lines in our PBS node file. Explicitly set that as our host file. Again, look at the total number of GPUs on each rank. So this is different on Polaris versus Theta GPU. The command is the same, but the output will be different. So on Polaris, for example, there are 4 GPUs per rank, whereas on Theta GPU, when you're on the full node queue, you have 8 GPUs per rank. So same command, but it will output a different number, for example, between the two systems. Again, calculate the total number of GPUs just by multiplying the total number of ranks by the number of GPUs on each of those. Figure out which MPI command we're using to launch the application. And then again, specify some arguments which will be passed to MPI that are unique for Polaris. So again, we explicitly specify that we want the entire environment that we're running in to be forwarded to all of our workers. This specifies the total number of GPUs. This sets the MPI CPU binding depth. This argument specifies the number of GPUs on each rank, and this is the host file. Again, so sorry if this is overly detailed, but just hope maybe it's insightful, or maybe people get a better idea of how things are working. And so when you see problems, then you might be able to more quickly figure them out. And And then otherwise, if you're not running on either Polaris or Theta GPU, it'll check to see if, so this is actually redundant as well. But if you were, for example, running this script on your local machine, a MacBook or something, for example, and you have an environment with MPI run installed, this would also pick up on that, for example. And so actually the only limitation, I think, in this, the only thing preventing this from being ran on your local machine, this example specifically, is the data set, which is obviously located on Lustre. But if, for example, you wanted to modify things and point to some other data set, this should work on any other resource as well. Then I have some kind of basic logic in here to try to make sure that we find the virtual environment directory and then make this local install of this AI for Science package. And so this is, yeah, just a nested else loop to make sure that we can try to find one, and then it will then install this package into that directory. Again, these are just some environment variables. Some of this is probably unnecessary, but I can change these now. And then this is some logic about specifying where the logs will be written to. So in this example, we write them out to, we create a directory inside this directory that we're currently in named logs, and we write our log file out to some .log file inside that directory, which has this timestamp, what host it's being ran on, the number of GPUs, CPUs, things like that, which is just useful for when you're going back trying to look at things later on. You can get and see exactly how things ran at the time that you ran it. We keep track of that log file in this file that you can always look and see which log file in this directory has been most recently modified. And then just print out some of this information so that you can see it in the log and you know where things are, make sure things are working correctly and everything's in the right spot. Then I can define the overall executable to be ran. So again, this is just my MPI command, which on Theta GPU is MPI run, on Polaris is MPI exec. And then the flags that we formatted that get passed to that MPI command, and then Python, whichever Python that we're actually using, and then the main executable, which in this case is just that main.py file. It should be this. Once that's kind of all set up and formatted, this again just prints out some additional information so you can see, make sure everything's working as expected. And it then will run that executable file, take in whatever arguments you specify, write that output to the log file specified, and run the job basically. So hopefully this should all work. Hopefully that maybe provided a bit of insight into the details of everything, but hopefully you should just be able to then run it as so. So we execute this main shell script and write the output to this main.log file, redirect the error and output to the same output stream, and send the process to the background. That's what that final ampersand means. And so that will immediately start writing the output of that script to this main.log file. You see this will kind of, so I think, as Kyle mentioned earlier, there are some issues with the file system being slow today. Hopefully that doesn't impact the live demo. So you can see now it's trying to make sure that it can install this package into the AI for Science, and basically it installs everything inside that source AI for Science directory into a package called AI for Sci. Then it prints out some things to make sure everything's working correctly. So it tells you where you're running things from, the log directory, and then the log file that the training will actually be written to. So this is maybe the most important line to keep track of. Then it just prints out some additional information. So you can see that it's starting a new run on 8 GPUs. Well, it should say 256 CPUs. Again, just maybe because I'm neurotic, it prints it out again. Just so you kind of can see how everything's running and making sure everything is coordinated and running how you would expect it to. So you can see the full details of what will be ran here in this exec line. So you can see it runs this MPI run, and then it passes all of the arguments as we had formatted. So the total number of GPUs, the host file, the number of GPUs on each rank, and then the environment variables that we specified. Then it finds the path to whatever Python we're using, the executable main.py file to actually run. In this case, we didn't pass any additional arguments. Otherwise, they would be included here at the end. And so that basically is the end of that output. As I mentioned, the actual output of the log from the training will be written out to this separate file. So what you can do to actually view them both is tail. So this tail-f command that essentially means to follow the outputs of whatever file it's passed. So in this case, we'll watch the end of that main.log file and then the end of this log file, which is so you can see it seems to be starting up and then begins training. So this is all kind of verbose information about the MPI initialization and communication. But then you can see it also gives some, I think, harmless warnings that can be ignored. And then goes on to give some information about the distribution and how things are initialized, so on. And then you can see it starts the training. And kind of gives this nice formatted information. So what epoch currently, the time for each step, the running loss, batch loss. The running loss is the global loss across each epoch, whereas the batch loss and batch accuracy are kind of local to this batch. And so you can see that this will then basically continue training for one epoch, which is just set by default in this configuration file, but can be overridden on the command line. So I think I have instructions for that here. So yeah, for example, if you wanted to change the batch size, for example, you can just pass that directly to the main shell script. If you really want to be detailed, you can keep track of the different log files when you pass different configurations and things like that. And yeah, it'll essentially basically continue on training. I think it runs validation at the end of each epoch. So at the end of this, which it doesn't look like we'll probably have time to finish, it will then run a validation step and print information about the validation accuracy and things. And so so the first goal, I guess, for homework would be to make sure that you can get this running. Just maybe using the default configuration on whatever resources you can get access to. So obviously, as over the next week, things will free up and people can try to get onto different systems, hopefully Polaris. And this should all work. So for this example, obviously it's just running on a single node, but all of the framework, all of the kind of infrastructure and things are designed to scale up across however many nodes you may have, for example. And so the homework maybe would be to try to get it running on more than one node if you're able to get access to that resource. Otherwise, obviously first goal being to get it running and then to try to find the largest batch size you can use essentially before you run out of memory. So that you will probably hit that pretty quickly. And really that's kind of an additional goal. Really, if you can get it running and submit a log file from a run, that is more than sufficient for homework. But if you really feel like going above and beyond, you can try to play with the batch size, the number of epochs, see how large of an accuracy you can get. Again, this is an actual kind of real non-toy model example, so the training will take a bit of time. Obviously, you can reduce the total training time by scaling up the number of workers. And so really the goal being just to try to play around with different configurations, different number of nodes, trying to change the batch size. If anybody finds anything that works particularly well, obviously feel free to share. But hopefully that, I haven't been checking Slack. Hopefully there aren't any other problems. If there are, obviously people can interrupt, or I'll stop now and take questions.
Folks can feel free to raise their hand in Zoom if they want, if they have questions. Obviously, also feel free to drop things in Slack.
So the homework, like how do we submit the output results with this one, or we have to give it as a file, or how does it work?
Yeah, so I was going to try to set up the homework so that depending on the amount of problems people were having with running things was going to kind of dictate what I wanted people to try to do. So if everybody was running into problems and couldn't get it running, then I was just going to say, get it running, show somehow that you got it running, that would be fine. But if it seems like if people are kind of actually able to, so any kind of screenshot example, you can include the entire log file, any sort of proof that you were able to get it running will, for the sake of completeness, is fine for the homework. Obviously, this whole process is designed to be a learning experience for everybody. So really showing me that showing somehow that you were able to run it successfully is more than enough. If you really, the goal being to try to play around with it and change things as much as you can. So, anything above and beyond that is also welcome. But yeah, really at this point, if you're able to get it running, and especially if you can get it across multiple nodes, that would be, yeah, perfect. But I also obviously understand that the resources aren't available for everybody all the time, and people's free time may not coincide with when resources are available. So if you can find some free time to get it running at all and submit that, that's more than enough. And I'll be more explicit about that and send something in the Slack channel explicitly mentioning that, as well as update the GitHub repo. So.
Thank you.
No problem.
Sam, it looks like we do have a couple sort of questions or errors, if anything, in Slack that you might want to address right now.
Oh, yes. I probably shouldn't put on the screen. Looks like a question about homework in general. Why is the accuracy so low? Let me see these questions now. Yeah, okay, so yeah. So the accuracy being low, again, that's just the consequence of this being, if this were running on MNIST, for example, those accuracies would be, up above 90% by that point, I would imagine. But again, it's just a lot of data, and it's trying to train on the ImageNet data set. So that's, yeah, as Kyle mentioned, there's 1,000 classes, so it's hard to really get good accuracy. And so really to get to good accuracy, again, you'll need to really increase the number of epochs and let it kind of continue training for a while. Okay, hopefully I addressed all of the problems that I see in there. If there's anything I'm missing, obviously people can raise their hand or at me in the Slack channel. Yeah.
Sam, the main.sh should be on a compute node.
Yeah, exactly. So that should be ran directly from a compute node. So from an interactive session or an interactive job, for example. Yeah. I don't want to, I think it should work as a batch script. So you should be able to submit that directly using QSub, but I haven't tested that. So I'm a bit reluctant to officially say it, although I guess.
So is that okay? We open a terminal and run the main.sh? Is it okay to do that way?
Oh yeah, yeah, definitely. So yeah, from an interactive job, yes, exactly. Just run that. You can just run that main.sh directly. You could, I mean, also if you're in an interactive job and want to run it directly, so you could also, I'm not sharing my screen anymore. You can kind of tease out the commands that are being ran and run that MPI run directly as well. It has the same effect. It just doesn't write everything to the log file and things like that. Did that answer the question? Sorry.
Yes, definitely. Yeah, thank you.
Thomas in the Zoom chat asked whether the question about the out of memory error was addressed, and if anybody could give a quick summary.
Yes, so I saw that actually. So has maybe it's weird to ask, but has anybody else gotten that issue? So I think Kyle said he was able to run it successfully with the default arguments and it didn't run out of memory. The only thing I could think is maybe if you had tried it once before and that job is still currently running. So you can, here, I'll send it in Translational. If you type, for example, jobs and you see, it'll say like, I don't know, %1, something. You can kill that if that's like a non-zero. So if you already have one running, that might be causing the out of memory error. Otherwise, I think it should work with the default configuration on a single node. If somebody else has another, or an example, and if somebody else can back it up and prove me wrong, then that would give me somewhere to try to figure out what the root cause of the problem is.
I'll try it again. I restarted the session on the node, and the current one is just waiting for the initialization, probably because the file system is a bit slow. But I wasn't sure. I had to step away. Sorry, I missed it if you talked about it before. Thanks.
Okay, yeah, no worries. And yeah, let me know. So yeah, let me know. Hopefully it works now this time. I've generally find that turning things off and back on again is a good way of getting rid of a lot of your problems. Not always though. So obviously if it doesn't work, ping me on Slack and I will definitely try to get it worked out for you.
Well, I think we can sort of pause again for if there are any more questions that people have immediately. If not, obviously continue to sort of populate Slack with things as they come up and we will address them there. But I think otherwise, unless you have anything more, Sam, I think we can give back 12 minutes of everyone's day and end a little bit early. Obviously, folks can continue to work and sort of go from there.
Yeah, sounds good.
Cool. And one thing as sort of a logistical question that I want to address, somebody asked, how can we know if we've submitted all of our homeworks? You should be, I think you're getting pings every time you submit a Google form, so you should potentially be able to look at that. And if people are like, I don't actually know where anything is, it's in my junk mail, whatever, DM me on Slack and I'm happy to sort of look and see how many homeworks folks have submitted if you don't remember immediately off the top of your head, just to sort of figure things out from there, sort of making sure that everybody gets in what they want for getting the certificate of completion and the digital badge at the end. Wonderful. Okay. Well, goodbye all. See you all next week for our very last session. Very exciting. Bye.